Good day, students. It's class time. I am Devalian Green, and with me is Sean Myers, and we will be guiding you through CSEC Industrial Education this week. All right, we are going to be looking at semiconductors. All right? Now, as students of electrical technology, right, we would have established the knowledge of what are conductors, right, and also what are insulators. Based on your prior knowledge, you would have known that a conductor is a material which permits the flow of electricity, while on the other hand, an insulator is a material which resists this flow. Now you may be thinking, what is a semiconductor, right? In order for us to understand the concept behind this, let us look a little at the electron theory of semiconductors, right? We will also be guiding you along, and there are certain key terminologies that you must understand in order for you to keep up, all right? So what are semiconductors, right? A semiconductor, this is a substance which possesses a resistance level between that of a conductor and that of an insulator, right? Now, as we mentioned earlier, we talked about the atomic structure, the electron theory behind semiconductors. Now, based on the topic or your prior knowledge, you would have known that a conductor, right, is a material which on its outermost shell, right, we're talking about the atoms. On the outermost shell, which makes up a conductor, it has less than 3 electrons, right? If it has 1 electron, it is considered a good conductor. If it has 3 electrons on its outermost shell, it is considered a poor conductor. On the other hand, with insulators, these have more than 5 electrons on its outermost shell, right? If it possesses 8 electrons on its outermost shell, which would be its maximum capacity, it is considered to be a very good insulator, right? If it has 5 electrons, it is considered a poor insulator. Now, for semiconductors, these materials have 4 electrons on its outermost shell. So therefore, it is in between that of a conductor and that of an insulator. Mr. Myers?
All right. Really want to say thanks to you, Mr. Green, for giving our students an overview of what we're going to be discussing today. Now, as we look at our slide, you know, there are certain terminologies that we're going to be using today, students. There are certain terminologies that we're going to be using. So one of such terminology is the crystal lattice structure. That is one thing that you're going to be coming across. So these are things that you want to write down. The definition for these things are very important to CXC, because as you are going to be talking about, you know, semiconductors, then these terminologies are very, very, very vital. So the crystal lattice structure, what is it? When we talk about covalent bonding, that's another terminology. Intrinsic, extrinsic semiconductors. Doping agent, dopant. Another terminology that we're going to be using is impurities. Majority carriers, minority carriers, holes, electrons, donor, acceptors. Now these are things that you will be hearing us referring to as we go through our presentation. Now, as we go through our presentation and these words come up, then you want to take note of the definitions for these words. Now, as Mr. Green said earlier, in order for us to understand semiconductor, then we must go back to the theory of electrons, the electron theory. Now, join me as I go on the board over here, and I'm just going to put a little simple atomic structure on the board. Now, one thing with electrical, we are concerned about the outermost shell, which is the valence shell. Now, as Mr. Green mentioned, if we have 3 electrons on the outermost shell, then we realize that the material that we're speaking to is a good conductor of electricity. It's a conductor of electricity. Mr. Green went about, highlighting that if it does have one, then it would be a very good conductor. If it has three, then it's a poor conductor. Now, when this outermost shell has 4 electrons, then that is what we're going to be talking about today, semiconductors. And that is where, our topic comes from, when it has 4 electrons on its outermost shell. Now, if it has more than 4, then we are now moving into the capacity of speaking about what an insulator is. So we understand, students, where, the term semiconductors come from. Now, semiconductors, as was mentioned earlier, it only has 4 electrons on its outermost shell. It is midway between that of a conductor and that of an insulator. It is midway between that of a conductor and that of an insulator. If we look on our chart, you notice there that we have a resistivity chart. And when you look at the conductors on a resistivity chart, like silver, gold, and carbon, then it has a very poor, it's times 10 to the negative 8. That is the resistivity, because these are materials that allow current to actually flow easily through them. Then if you look at, times 10 to the 2, times 10 to the 4, like silicon and germanium, which are commonly used semiconductor materials, then you realize that it is midway. And then if you move on into the higher categories now, like times 10 to the 10, times 10 to the 14, times 10 to the 18, then this is where now we're speaking about our insulators. And good insulators are like glass and quartz and rubber and so forth. Now, I'm going to ask Mr. Green to go through with you an explanation now of some of our most commonly used semiconductor materials. So what are some examples, Mr. Green, of some semiconductor materials?
Now, once we start referring to semiconductor materials, right, some of the most commonly used are silicon, right? You have germanium, and you also have what we call gallium arsenide, all right? These are well-known materials that are used for semiconductor purposes, all right? Now, let's take a look at silicon. Now, silicon is obtained from silica, and as you hear that term, you should be thinking of sand, right? Now, it has what we consider to be a high resistance to voltages and temperatures, right? All right, its temperature and resistance does not change much when it is heated, and that is very key to note, as you know that, or what we will be discussing, temperature does have an effect on semiconductor materials, all right? Now, its potential barrier is about 0.6 volts, all right? Now, let's look at germanium, right? Germanium is obtained as a byproduct from the flue dust of the zinc industry, all right? And the electrical conductivity of germanium is higher than that of silicon, right? And it has more optical characteristics, right? The potential barrier is also smaller than that of silicon, for it is about 0.2 volts as it relates to germanium.
All right, so thank you very much for that, Mr. Green. Now, as we move on, we're going to be looking at, the arrangement of our semiconductor materials. Now, our semiconductor materials, as Mr. Green mentioned earlier, silicon and germanium, they are arranged in what is called a crystal lattice structure. And atoms, it occupies sites at the nodes of the lattice. Now, as we look at, the examples of our semiconductor, the categories that they fall into, then we have 2 categories. We have intrinsic semiconductors, and we have extrinsic semiconductors. Those are the 2 broad categories that they fall into. Now, students, as we mentioned, it is very important that you take note of these definitions. So an intrinsic semiconductor material is actually a pure semiconductor. That means it is only made up of silicon. It is only made up of germanium. So it is free from any impurities. But we're going to realize that there are challenges with it. It is not workable. We're going to be realizing that as we go along. So as a result, now it moves us now to our extrinsic semiconductor material. Now, extrinsic semiconductor material is where you actually add impurities to it to ensure that it is workable. It can conduct electricity. Now, some examples of our extrinsic semiconductor materials are our N-type semiconductor and our P-type semiconductor. And the aim of our discussion today, we're going to be hoping that we can draw the crystal lattice structure, because we don't want to just be presenting information to you students. We want for you to be able to retain the information. So we'd like for you to be able to draw the crystal lattice structure, and we're going to be having a discussion now as to how we come up with the N-type and how we come up with the P-type semiconductor material. But let us focus a little on our first, which is the intrinsic semiconductor. Now let us talk a little bit about our intrinsic semiconductor. Now, our intrinsic semiconductor, we mentioned that you have interatomic spacing. And these interatomic spacing, it actually occupies, the shells, the outer shells, the valence shell of the atomic structure that we mentioned about. Now, these linkages form what is called covalent bonds. And these are formed at the outermost shell. Now, as we looked at our atomic structure earlier, we realized that semiconductor materials actually has 4 electrons on its outermost shell. Now, from your chemistry class, you know that in order for the shell to be complete, then it needs to have 8 electrons there. It needs to have 8 electrons. But there's a beauty about a semiconductor material. Since it only has 4, then it is not going to be giving up any electrons, and it is not going to be readily accepting any electrons. And that is why it is so hard to work with intrinsic semiconductor materials. Now, covalent bonds, a very important terminology. These are forms when individual atoms share electrons of their neighbors. So that is what covalent bonding is, students, where you have individual atoms sharing the electrons of its neighbors. It's very important to note that the number of holes is going to be equal to the number of electrons. Now, as we look at this slide that you're seeing, we can realize there the covalent bonds that we're talking about. So silicon atom, you notice that the atomic number is 14? And it has 4 electrons on its outermost shell. But we are not so concerned about the atomic number. There is no need for you to, you can just save that, for future reference. But in electrical, we're not so much concerned about the atomic number. What we are concerned about is what is happening on the outermost shell, the valence shell. So it has 4 electrons on this valence shell. And when we come back, we're going to be speaking to you a little bit more about the intrinsic semiconductor. So when we zoom in, you're going to be drawing this lattice structure very soon. So I encourage you please to get out your pens and your papers and your pencils, because we want to ensure that you retain the information that we're referring to. So when you zoom in, you notice there that covalent bonds are identified. So we have 4 electrons on its outermost shell, but the one that is in the center, then it is picking up 4 electrons from its neighbors. And that is what covalent bonding speaks to, the sharing of electrons. Now, this is what happens in an intrinsic semiconductor. But as we mentioned to you, there's a big problem when it comes to the intrinsic semiconductor. The conductivity is too low for most purposes. So it's hard to work with. We can't really do much with it. And that is the reason why now we have to move on to the next type of semiconductor that we have, which is actually the extrinsic semiconductor. Now, with the extrinsic semiconductor, it's not that we have a different material working with. It is the same silicon, it's the same germanium, but in order for us to actually make it workable, then what we have to do is to add small amount of impurities to that pure material. Small amount of impurities. Now, on our slide, you notice that there's the next terminology that we come across, which is doping. And that is what doping is, students. Just adding small amount of impurities to that pure semiconductor. But here's the question. Where will you get the material from to add to the pure semiconductor? Where would you get the dopant from? Well, as we mentioned earlier, that the semiconductor, silicon, germanium, these are group 4 elements. They're group 4 elements. So in order for us to get the impurities, then the impurities have to come from a neighboring element. So the neighboring element to a group 3 is actually the neighboring element to a group 4 is actually the group 3 and the group 5. And that is where we'll be getting, the impurities from. Now what we're going to be doing is that we're going to be moving to our board. And we're going to be going about drawing, our first intrinsic semiconductor material. Let us see if we can carry out that activity together. Let us draw our intrinsic semiconductor material. So that is what we're going to be doing. We're going to be drawing our intrinsic semiconductor material. Now, as we mentioned earlier, our intrinsic is a plus 4e element. And let us say that we're just going to be utilizing a few of them. So all of these are plus 4e, plus 4e. Now, we mentioned earlier that you have covalent bonds. So let us put in our crystal lattice structure linkages right here. So these are linkages, students. All that we have in blue there, those are our linkages. We missed one right here, so let us just put that in. Now we're going to be getting a different color. And what we're going to be doing now is to show you how we actually get our electrons in. So let us use the one that is in the center first. So this, as we mentioned, has 4 electrons. So one there, one there, one there, and we have an electron right here. So you notice it has 4 electrons that makes up, the silicon atom. But if we note this one right here, then it is also going to have an electron here. It will have another electron right here, one there, and one that is there. That is how it will get its 4. But if you notice that this electron that we have right here, it belongs to the silicon atom. But it is now doing what? Sharing. And in the same process, this silicon atom is also sharing. So as a result of the sharing, then we will have now all shells participating in what is called covalent bonding, which is a sharing of electrons. So that is what we will have. So this is now an intrinsic semiconductor material, free from any impurities. And we missed out our plus 4e right here. So let us zoom in on our board now, students, and see if we can understand our intrinsic semiconductor material right here. So you notice plus 4e, pure silicon. This is a crystal lattice structure that we're talking about. And we have covalent bonding taking place. Pure intrinsic semiconductor material. Now if we move over back to our PowerPoint presentation, then on our PowerPoint presentation, you notice that we actually move over to an extrinsic, where we add an impurity to the crystal lattice structure of the silicon. So the impurity came from a group 5 element, and that impurity is actually antimony. It has 5 electrons on its outermost shell. Now if we should actually go back to our board, and on our board, let us say that we're going to be removing one of these silicon atoms, and we're going to be adding what is now a plus 5 element. Let us now add our plus 5 element to our board. That is what we now have right there. We add our plus 5 element. Now remember, we would have 1, 2, 3, 4. All right? So we'll have 1, 2, 3, 4. This would have been here from earlier. So that would have come from that element over there. So we have 1, 2, 3, 4. But what is missing? We have one more element, which is a 5th element. So this is an element which is free. This is now we now have a free electron. That is, now we have a free electron. And that electron now is able to actually wander about in this crystal lattice structure, bouncing other electrons out of their place. Now remember, from our studies of electricity, the movement of electrons is what current is. The movement of electrons. So this free electron, it is able to move here, not this one out of place, this one is able to move, and it is wandering about in the crystal lattice structure. Now, for a semiconductor material, we will know we could dope it with a few other, group 5 elements, and as a result of doping it with a few other group 5 elements, then you realize that what we will now have here is that it would have, 2 or 3 free electrons moving about, wandering about. And then as a result, now we're able to actually work with that structure. Now, this is now an extrinsic semiconductor material. Now, let us now move back to our PowerPoint presentation there. And we're going to ask Mr. Green to actually take you through a discussion now to identify the free electron right there on our board as we move over to drawing the P-type semiconductor on our whiteboard. Mr. Green.
All right. So as was discussed by Mr. Myers earlier, right, you would have looked at what are intrinsic semiconductors, and he just discussed the extrinsic semiconductor, in which you would then add a doping element, right? You would take an element from either the group 3 or the group 5, right? Now, in the previously mentioned process of doping, he added a group 5 element, right, which is antimony. Now, what you have happening is that based on the amount of electrons that is within or which is upon the outermost shell of the antimony atom, you would have the resulting free electron without a bond, right? Now, this free electron is now able to roam. And as Mr. Myers mentioned, and as you would have known, based on the electron theory, that the movement of electrons is what causes our current, all right? Now, this would cause what we call a N-type semiconductor, because what you have occurring is that the electron would become now our majority carrier. Now, it is negatively charged, right? Electrons are negatively charged. So that would give us our terminology or category, the N-type semiconductor. Now, we'll be moving on to another method of doping with Mr. Myers, all right?
All right, so we're still at our extrinsic semiconductor. And now we're going to be focusing on our P-type. So we're going to be looking at our P-type, and we're going to be drawing our atomic structure or crystal lattice structure for our P-type semiconductor material. Now, as we mentioned earlier, we have our crystal lattice structure. We have our crystal lattice structure, and we also have the covalent bonds being formed, which is the sharing of electrons. Now, in order for us to actually benefit from the P-type, remember, we're going to be doping with a group 3 element. And an example of a group 3 element is actually boron. So we're going to be doping with a group 3 element. So we know that right here, we're going to have a plus 3e element, which is going to be our group 3 element. Now, for it to have plus 3e, then we're going to have one electron right here, one there, and we're going to be having another electron right there. But for right here, we're going to be having what we call a hole, because that is going to be void. Because since it is boron, we will only have what? 3 electrons. Now, for our silicon, remember we're still having a silicon structure here, so it's plus 4e. We're going to be having one electron there. One will be there, one will be there, one will be there. but then now the other shells will be filled out with neighboring electrons. So we can safely put in the other electrons because we know that they're going to be sharing electrons from their neighbors. So +4, +4. So this is our crystal lattice structure. So we actually hope, students, that you're actually drawing this structure. It's a little bit tedious to draw, and you have to be doing it over and over. But let us see if we can actually zoom in, because the crystal lattice structure for p-type is different from that of the n-type. For the n-type that we mentioned earlier, you had the +5e element, you have a free electron wandering about. But for this structure, you notice we have a what? +4e. So we're doping the silicon with boron. Boron comes from a group 3 element. So it has 3 electrons on its outer shell. Now, having the 3 electrons, then what we realize here is that we have a what? A hole. We have a hole. Now, we refer to this hole as being positively charged. So the majority carriers in a p-type semiconductor, majority carriers would be what? Holes. So the majority carriers would be holes, and the minority carriers would be electrons. And we're going to be focusing on that a little bit later in our slide. So the majority carriers will be holes, and the minority carriers will be electrons. So this hole that we have right here, how will it actually affect our entire crystal lattice structure? How will we be able to get the movement of electrons taking place? Now, over the years, we have had a lot of debates about the holes moving. But one thing I want you to bear in mind is that the hole never moves. So this hole, it is positively charged. It's a p hole. It is always positively charged. So the electron is going to be attracted because the electron is negatively charged. So the electron will be attracted to the what? The p hole. And as a result, this electron that we have right here will actually take the space right there. So let us do that. This electron that we have right here will actually move and take the space right there. So when it takes the space right there, then what is going to be happening? It will now create a what? A hole on this side. So it would appear to the naked eye as if the hole actually what? Moved. But in truth and in fact, what moved was the what? The electron. So this hole is right here. You could have an electron that is all the way up here. That would actually be what? Attracted to this positive hole. And then now the electron could jump from its shell and come right there, and it just creates a what? A hole. So as a result of that, we realize now that we're actually moving. Electron is actually moving from one point to the next. So this is a crystal lattice structure, and it is very, sometimes tedious to draw. But if you go through the exercise of drawing it, students, then you get to familiarize yourself with doping. You get to familiarize yourself with, the covalent bonding that is taking place. And you get to familiarize yourself with also the electrons and the holes, the majority charge carriers and the minority charge carriers. Now, if you look back at our PowerPoint, our slide, then we realize our hole right there. So boron, we have the silicon structure. And we realize that, we have the hole that is actually free, and electrons can actually jump and, jump into that space. And as a result, you will have a space created elsewhere. So we have electrons that is actually moving. So just to reemphasize what we mentioned earlier, the p-type semiconductor, majority carriers are holes, the minority carriers are electrons. And when we look at the n-type, we actually have majority carriers being electrons and the minority carriers being holes. Now what we're going to be doing is actually look at our p-n junction. That is what we're going to be doing. Now I'm going to allow Mr. Green to actually speak to you a little bit about our p-n junction.
All right. So when we are referring to what we call a p-n junction, right, this arises when we take one p-type semiconductor and we will combine it or put it next to what we call the N-type semiconductor. Now, between these two materials, we will have forming the junction, the p-n junction, all right? And you're going to be realizing that based on the composition, right, of these two materials, there's going to be some activity taking place as a result of our majority carriers on both sides. As was before mentioned by Mr. Myers, for the p-type semiconductor, our majority carriers are the holes, right? The holes are positively charged. And for the n-type semiconductor, we have our majority carriers being our electrons, which are negatively charged. And based on your knowledge, you would realize that positive and negative, right, unlike poles or unlike charges, will be attracted, right? So this is what is going to be causing a phenomenon at our p-n junction. And now Mr. Myers will be giving you a bit more information as it relates to the p-n junction.
All right. Now, we want to just quickly put on the board, students, you know, what will be happening when we actually fuse a p-type and fuse an n-type together. So we know the p-type is positively charged, so we're going to be using these, you know, holes to actually refer to our positively charged p-type. And we know that our, you know, this is our p-type. And then we have our n-type. And that is where we actually end up with our what? p-n junction. That is where we end up with our p-n junction. So these are electrons that we're going to be having over here, and our electrons. Now, right across this barrier, we realize that we will have, you know, this is where they fuse. This is where they fuse. So across where they're fused, we refer to it as a junction. But right across our junction, what we will have naturally taking place is actually space charges. So over here, we have an increase in holes rather. These are positively charged. So what we will realize is that these positive charges will just wander over to where, you know, our electrons are, because they have the laws of attraction taking place. And then now we will have these negative charges wandering over to where our p-type is, because we have, you know, attraction taking place. So what we're going to be doing is to encourage you to read up on these things, and you know, we are going to be looking forward to see you again in the near future.